Also, I have a question. Do we have to memorize all the arc integral rules or just like
Arctangent.
just like
Yeah. 13 from worksheet 1. Okay. Okay, so our formula is arc length is definite integral from a to b root 1 plus f prime of x squared. So here's our f of x, and our points, we only need our x values. So we need from 0 to 2. So that's all we need. We don't need that 1 and 49. So we just insert into our formula. F prime is going to be the derivative of our function. So 12x cubed plus 2x minus 2. So that's going to go in this space, bracket squared. And it says just set up, do not evaluate. So we can leave it like this. Guys, I'm just taking questions from any problems you want me to go over. Okay, which one?
it was 5 on the worksheet.
Oh, yeah, so it was an improper integral that also required us to do partial fraction. Yeah. So first we know that, oh, I gotta do limit as b approaches infinity. But I still have to figure out how to, find the antiderivative of this. So anytime you have multiple variables that are being multiplied and they're in factored form, we would ideally want to split them up into a over x plus b over x minus 1. So once we know that will make our problem easier to work with, then we just start going through partial fraction. So partial fraction, once we set this up, then we're going to cover up method. We find the factor here, set this denominator equal to 0. So this factor is going to be 0. I'm going to cover up x, replace the remaining fraction on the left side with 0. So 3 over 0 minus 1, that's 3 over negative 1. So a should be negative 3. Oh, I didn't carry that over, did I? Hold on. So a should be negative 3. So it should be negative 3 over x. Sorry about that. Was that what you were catching?
Mm-hmm.
Okay. So this ends up being negative 3.
I also was confused about like when it diverges and when it doesn't. Will it only diverge if it looks like one of these like a cover up method?
Hold on, let's see if I fix that and then put it.
I didn't know what do you mean? Is it just like when you do
Is there now that makes choice?
Something that they say is it's an actual thing. How many freedom of what to do is if any difference. Which means I see what she's saying. And if you put like euro or regular, what does that?
Okay, sorry. I did fix it. I did go over it in class because I did mention that the key was wrong. So let me go through it again with this problem. So, okay, so this is number 5 on worksheet 2. I fixed it on the website and Yeah, so let me go over. So A is -3, B is 3. So we're at this stage, right? We know that both of these we can find the antiderivative using natural log. So this is -3 natural log of absolute value of x plus natural log absolute value of x minus 1. Right. Now, anytime we have a subtraction using logs, I want to rewrite it in this form here. We can take advantage of log properties. So we know that we can factor the 3 out. I can write this as natural log of A over natural log of B. Sorry, natural log of A over B, because this is natural log of A minus natural log of B. So if I factor the 3 out, I'm able to get it to this stage. Okay, makes it easier to interpret what's happening with that infinity. So now that we're here, okay, then we can plug in upper bound minus lower bound. Okay, so are we good up to this stage? Okay, now we're gonna do limit as b approaches infinity, okay, of this expression minus this. So basically, anytime we have infinity, we just want to figure out, is this going to give me something that is a real number, or is it going to stay as something that is going to be infinity? Anytime infinity shows up in your evaluation, then we can say it diverges. Anytime infinity or non-infinity it shows up. But with this problem, we would have to get it into this form first, because if you plug in, if you try to evaluate separately, you're going to get natural log, you're going to get infinity minus infinity, and that's going to feel like we don't know what to do with that. So we do want to get it into this form before we evaluate what's happening. Now, this here, we're able to interpret that being 0 because, let me ignore that infinity for a second. What if I did limit, or let's, yeah, ignore that natural log for a second. What is this equal to here? Or let me ask you this, when we're thinking about horizontal asymptotes, if we're doing limit approaching as b approach infinity, what do we do here? All right, let me do something that may be feeling more familiar here. Limit as x approaches infinity, 3x squared minus 3x plus 4 over 5x squared minus 1.
If you take the exponents like to it.
So here, do the degrees match?
Yeah.
Yeah, the highest degrees, right? So we just take the ratio of the coefficients. So limit of this is what?
If the
So what's the limit of this?
it would be 1, right?
It'll be 1, right? Because the degree is 1, the highest degree is 1, the coefficient is 1 and 1, so that's equal to 1. Okay, does that make sense? Now, if the limit of this is 1, then I know that this must be equal to 1. What's the natural log of 1? 0. So that is going to allow my answer to converge. So I'm going to be able to get down to a real number here.
And then if the degree in the numerator is higher than
The denominator, then it'll go to infinity.
if it's in the denominator.
Yeah. So
What happens if it's in
if sorry. If it's in the denominator, it'll go to 0. So if I was limit as x approaches infinity of 3x squared minus 5x over 5x cubed, that's equal to 0. And if it was limit as x approaches infinity, 3x3 plus 4 over x squared, this is infinity. Yeah, you compare degrees. If degrees are the same, you take the ratio of the coefficients. If the degree in the denominator is higher, then it's always going to be 0. If degree is higher in the numerator, then it's going to be infinity. And even if it feels like, oh, I'm memorizing these ideas, you don't, if you just kind of think about it logically, this should make sense, right? If the degrees are the same, then we know that numerator and denominator is basically evening out. They're both growing at the same rate. It's just at the ratio of 3/5. Here, my denominator is growing at a much faster rate than my numerator. So if the denominator is getting larger faster than the numerator, then I know my fraction is getting smaller and smaller towards 0. And if my numerator is growing at a faster rate than my denominator, then this overall value must be growing larger and larger towards infinity. Yeah, this one was wrong on the key and we did go over it in class, but yeah, it's good to revisit this. Yes.
For all the limit problems, like 10, 11, 12,
Mhm.
they all went down to y=1.
Mhm.
Just expect that.
Not necessarily. So yeah, I mean, the ones I found to review with, those all ended up being one, but we can do one where it's not always going to be one. Okay. So this was on the on page 15 of your notes. This is L'Hopital's rule, but we can do one. This is part A, so I'll walk through part A, or have you guys try A and see how you do with that. So I'll put that here. Okay, that's a copy this down somewhere. Try this. Okay. They're very good up to this point here. Okay. Okay, so now that I'm gotten that right side to be a numerator over denominator, I can we want to see if L'Hopital's rule can apply, and if we can evaluate the limit and get in indeterminate form like 0 over 0 or infinity over infinity, we know that we can set the stage to do L'Hopital's rule. So if I plug in a really large number, let's say you know, 1,000,000 or you know, something that's in an infinity range, you know that 2 over infinity is going to be 0, and 0 plus 1 is 1. Natural log of 1 is going to be 0, so numerator is 0. Denominator, 1 over infinity, right? If my denominator is really, really large, then my fraction is really, really small. So 0 over 0, this is an indeterminate form that is allowing us to do L'Hopital's rule.
It's good.
Oh, sorry. Right. So if we want to do L'Hopital's rule, then I want to set my expressions up for me to find the derivative. Numerator is going to be u prime over u, and denominator is just going to be power rule. Okay, but I want to move the x to make it easier for me to apply my derivative rules. So okay, so now I'm just going to do u prime over u. So u prime is going to be negative 2x to the negative 2 over this u value. So that takes care of my natural log portion. X to the negative 1 is power rule. Now I could try to evaluate the limit, but I find that if I can just clean this up a little bit more, then I can maybe do this a little bit later. So I'm going to try to clean this here, clean this up here. I see a bunch of these negative exponents. I don't want to compound the effect of turning them back to positive exponents, because then I have a really complicated complex fraction. What if I just try to reduce this complex fraction first and then see where that leaves me? So dividing by an expression is the same thing as multiplying by its reciprocal, right? So I'm gonna see if I can just do some cleanup within this messy fraction. So dividing by this, same thing as multiplying by the reciprocal. Now at this stage, what can we do to reduce this expression? Yeah, this is nice, right? To be able to take this out. Yep, that's right. These two negatives cancel out. So I'm left with -2 over 1 plus 2x to the -1. So now I think this will be easier to evaluate at this stage. I can maybe do a little bit more cleanup here. Sorry, you're right. This will be positive. 2 negatives, yep. So now I'm at the stage here. I'm going to plug infinity in for x here. 2 over infinity, that's a really, really small number. That's going to end up being 0. 0 plus 1 is 1. So I'm left with 2 over 1, which is 2. Okay. We're not quite done with the problem yet, because that only takes care of the right side. We still have to, we're doing log differentiation, so we have to resolve that natural log on the left side. So the natural log of y is equal to 2. Raise both sides with e as the base. Drop that e in natural log, so I have y is equal to e squared. This is my limit.
When you're plugging infinity, it's just kind of like, that's about this much, right?
Well, it depends. You know, like we kind of have to think about what's happening with infinity, right? So 2 over a million, 2 over a billion, what is that value getting closer to?
It's getting smaller.
Until it reaches 0, right? Over here.
If the limit is approaching 0.
If limit is approaching 0. At what stage? At this stage here?
Yeah.
So if its limit as x approaches 0, then I don't.
It would work for the problem.
Yeah, I don't.
Okay. But for there, you just do the same thing.
Yeah. You just plug it in and you see. You're hoping that you can get down to this stage.
Yeah.
Either infinity or infinity over 0 over 0, so that you can do L'Hopital's rule. Yeah. So the problem I give you, it will fulfill this requirement. You just have to make sure you show me that.
Okay.
Yeah. Yeah. Let me do one that I was doing yesterday in the help session. Let's try. This is from I think from one of the notes problem from the notes page. I think this will demonstrate, especially how to deal with, like, how do we do why, when do we do one-side limits? When can we just plug in? And when is it diverge? When is it converge? So let's try this one here. Let's see. Well,
One over dx.
it's 1 over x, right? Yeah, thanks. Okay, this doesn't look like it's, there's no infinity in our bounds, but we know that there's an issue with 1 over x, right? There's a vertical asymptote where at 0, and it is impacting my bounds, right? I'm trying to cross over a vertical asymptote, and that's forcing me to have to split my problem up into 2 separate integrals, one that is to the left of the vertical asymptote and one that's to the right of the vertical asymptote. So let's split it up. Now we have to be better about how to deal with the bounds, because the bounds right now, that 0 is doesn't make any sense, because we know that the bound is right at that vertical asymptote. So we're going to use a limit notation to indicate that so we know that the graph is going to exist on both sides of the vertical asymptote, right? So the graph looks something like this. I just want to kind of give some visual connection in terms of where we place our one-sided limit. So this one is going to be limit as b approaches infinity from -1 to b. Sorry, limit as b approaching the asymptote 0. Of 1 over x dx. Now notice that this is going to be to the left of 0. So we're approaching 0 from the left side of 0. So this is going to be 0 to the left. Meanwhile, we're approaching 0 from the right side of 0 on this one here. We'll put a plus here. Integral from b to 1 over x dx. So these are independent problems. I'm going to handle them separately. And then in the end, if any one of them shows up with infinity, I know I can say it diverges. But if I'm able to get real numbers out of all the evaluation, then I can converge and have an answer. Okay, good so far. Okay, so what's the integral of 1 over x? Natural log as value of x. Evaluated between -1 and b. So okay, we'll deal with this later. Let's take care of this side. Same thing, right? Natural log as value of x. All right, good so far. Now, the first thing we do, whenever you see a one-side limit, ignore the one-side limit to begin with. Just insert in the value that you see. Okay, so I'm going to plug in 0. Now, does this make sense? Natural log of 0. What's natural log of 0? Undefined. Okay, so if you think about what natural log graph looks like, This is my natural log graph, right? There's a vertical asymptote at 0. So if my evaluation is getting me undefined, I need to dig a little deeper, right? Because right now that's not quite giving me what there is a movement towards 0. So let's pick values. So what are values to the left of 0 getting closer towards 0? Negative 0.1, even closer, negative 0.001, negative 0.0001. Okay, right? I'm getting closer towards 0 from the left side of 0. Now, if I plug these negative numbers into the absolute value, what's going to happen to these values? Yeah, become positive. Okay, so I'm going to treat these like 0.1, 0.001, 0.0001. So if I'm getting closer towards 0 from the left, now from the right side here, because it's positive, like 0.1, 0.001, 0.0001, what's happening to the y value?
Is getting.
Yeah. So this is going to result in negative infinity. This is probably going to diverge. I'm not going to be able to clean this up. So this is indication that I'm going to have to diverge. Okay. Now I'm going to do this one just for, and we already know it's going to diverge, but let's just do this side just for practice purposes, right? Okay, so here, natural log of 1 is 0. That's fine. Natural log of b, here again, I'm going to plug 0 in. Natural log of 0 is undefined, but there's movement to it, so I can, I'm going to evaluate a little further. So this one is going to be 0.1, 0.01, 0.0001. Same thing here, right? As I'm approaching 0 from the right side, natural log of b is going to be positive, negative infinity.
Would it be easier, or should we not do natural log of 1 over b?
Undefined.
It'll still give you,
Okay.
yeah. But even if this worked out, we would still say it diverges because this one is clearly not
Yeah.
getting us there. Yeah.
Yeah.
But yes, we could do natural log of 1 over b and evaluate that, and
Okay.
that should still get us the same thing. Well, the limit is talking about the x value, but natural log of b is talking about the y value. Like as we get closer towards 0, what's happening to the y value or the expression? The expression is getting towards infinity. So this diverges. So if you ever see a one-sided limit, plug in that real number first. If you can convince yourself that real number, that value is going to get you a real number, then you stop, then you can produce your answer and say that converges. But if something is undefined and it's a one-sided limit, then you can dig a little deeper and start looking at decimals and looking at the behavior of the graph to see if you can identify what the value is moving towards. Is it moving towards a real number, or is it moving towards infinity or infinity? And if it moves to a real number for everything, then converges. If it doesn't, then it diverges. Mm-hmm.
Same thing for number 6 onward. So you don't get a real number, so you look at the graph.
Yeah. Let's see. Number 6 on worksheet 1, this one here. So I talked about how we can use the arctangent graph, but we can also do this. Wait, which part are you talking about? This part right here?
Just the end. On third arctangent
Mhm.
over 3.
Yeah. So here we know that arctangent of is basically infinity, right? So basically saying now if we're looking at this graph, we can tell that as we move towards the right, this arctangent is getting up closer towards pi over 2. But even if we didn't know this graph, let's say we only knew what the tangent graph looked like, we can still arrive at the same conclusion. So arctangent infinity is basically saying tangent of what theta value is equal to infinity. What theta value will allow tangent to go to infinity? And here, if we look at the graph here, tangent of pi over 2 is where infinity occurs, because as you get closer towards pi over 2, that's where infinity occurs. I mean, it's also negative pi over 2, but we see negative pi over 2 is not within our interval. So it makes sense that that's where the vertical asymptote is. That's where my tangent is headed towards infinity, right around pi over 2. The most I give you with arc trig will be arctangent. I won't give you arcsine or arcsecant. Mhm. Okay, so we know that we're going to go from 0 to pi over 3. So that's our a and b value. We know we have to insert f prime into my formula. My f of x is this messy expression. So if I want to find f prime is a derivative of this integral. So that reminds us of second theorem, right? Second theorem allows us to clean things up. So I'm left with root 3 minus 4 sine x squared x. Everyone good up to this stage here. So this is my f prime. I'm going to insert f prime into the formula here. So 1 plus f prime squared. The nice thing here is I can get the radical and the root to go away. So I'm left with 1 plus 3 minus 4 sine squared x. Okay, so I have clean that up. I get root 4 minus 4 sine squared x. Now this feels like a complex problem. We're not going to be able to go through use substitution. And even if we factor out a 4, it doesn't quite clean up nicely. But maybe there's a trig identity that can help us with this. So we know that there's a trig identity that says sine squared plus cosine squared equals 1. And if I adapt that trig identity, what if I multiply my trig identity through with a 4? So 4 sine squared x plus 4 cosine squared x equals 4. Right, we know this is true. Okay, and now if I kind of play around with this expression here, 4 minus 4 sine squared x, if I rearrange this equation, I can say that 4 minus 4 sine squared x equals 4 cosine squared x. Okay, good so far. Now, the nice thing about this is if I have this as 4 cosine squared x, this I can evaluate. Right, before that minus sign is preventing me from taking the square roots directly. But now this is down to one term. I can just take the square root of this expression. Square root of 4 is 2. Square root of cosine squared x is cosine. And now I'm down to something that feels a lot more manageable. Okay, so now I'm down to this stage here. I want to find the integral from 0 to pi over 3 of 2 cosine of x. I know cosine of x turns into sine. So 2 sine of x evaluated between 0 and pi over 3. So 2 sine of pi over 3 minus 2 sine of 0. Now, 2 sine of 0 is just going to be 0. Sine of pi over 3 is going to be root 3 over 2. So I have 2 times root 3 over 2. The 2's cancel out. I'm just left with root 3.
for a differential equation.
A differential, like a logistic differential.
Yeah. Yeah, the biggest thing is just to be able to know how to manipulate your expression to pull that carrying capacity or that limiting value. So this is number 10 here, off of worksheet 2. So we have dPdt equals 1/5 P minus 1 over 2000 P squared, identifying the carrying capacity. We know that one form is that Ky times 1 minus y over L. So what I can do is I can factor out my P is kind of like my Y value. So I'm going to factor out my whole idea is that if I can get that 1 to show up, then I know I can get this form to be produced. So if I factor out a 1/5 P, I know I can have my first term being 1. And if I factor out a P out of this, I'll get from P squared, I'll get P. If I factor out a 5 from 2000, I get 400. So anytime you factor something out, it's always good to redistribute just to make sure that you can get back to your starting point and that you didn't accidentally factor incorrectly. So if I distribute through, I get 1/5 P minus P squared over 2000. So I know that this is fine. This is in the form of my logistic differential equation. My K is 1/5, my P is Y, 1, my Y is P, and my L is 400. So there's my carrying capacity there. Yeah. Yeah. Well,
I don't need like, to do a problem, but I was wondering for, I forget what it's called, but when you have the F and G prime,
Oh, yeah, integration by parts.
what's the rule again? Like, how do you know when you're doing the like,
That method.
yeah.
So, right. So what's the idea? So the idea is that, so this is this is the summary here. So use this original IBP formula if you see logs paired with something else. If it's logs and trig or logs or just log by itself. So for instance, if it was like integral of natural log of x dx, this is logs paired with quote unquote algebraic. So the one that's hiding is the algebraic. Anytime natural log is in the problem, I can't do tab method. I have to do integration by parts. Now, the way I would know to do tab method is if I see algebraic with something else, then I just prefer tab method. It's just a lot cleaner.
Yeah.
Right. So tab method would be something like, integral of x cubed, cosine of 2x. Or integral of x cubed and e to the 2x. Yes. Yeah, for tab method, algebraic is always f. Because what you want for tab method is you want your f to reach 0 so that you know how many times to take the antiderivative of that g. So yeah, well we know that tab method will always reach 0. If you look at page 1 here. Yeah. So you know that algebraic is always going to go, but natural log is not going to reach 0. So we're forced into having to go through IBP with f being your natural log expression. Yeah. You could, right. Number 3 is not a nested one.
Yeah.
But I think most students would just prefer tab method because it just feels cleaner, right? But yeah.
So you get once you turn it into
Numerator, denominator.
Yeah,
Oh, how do you know if something is going to infinity or going to zero?
yeah.
I think you just have to plug in a number and convince yourself what's happening there. So like this one would not quite fulfill L'Hopital's condition, because if I plug infinity in here, then I plug infinity is gonna be infinity. If I plug infinity into here, what's one over infinity? That's a really small number. Yeah, so, well, you won't see a scenario like this, but I'm just saying, you know, you have to show that it's either infinity over infinity or zero over zero. But I think this is what you're asking, right? It's like, how do you know if something is zero or infinity? This is an example. Yeah.
Another thing is, when it's the same function, you look at the, like, degree of the,
Yeah,
and if it's higher on the top, it's positive infinity. And if it's higher on the bottom, it's zero.
right. Yeah, so I had that sheet. Yeah, this example. Yeah, the degrees are the same. We take the ratio of the coefficients. If the degree is lower than the denominator, it's always zero. Degree is higher than the numerator, it's always infinity.
And do we need to know, like the growth rates, like, say you have a natural log on the top, like, I remember learning about it last year.
Not for this quiz, but yeah, it's LRPE. Logs grows the slowest, followed by radicals, polynomials, then exponentials. So if its limit as x approaches infinity of natural log of x over e to the x. Natural log of x is growing slower than e to the x, and because e to the x is growing faster, we know that a slower over a faster is going to be zero.
Wait, what is the?
Yes, slow, because like, it's like this one open, like slower, because like, if you can regard slower as like, you know.
Can you work through number 5 on the worksheet too, real quick? I think it's number 1.
Yeah, and this.
Yeah, this is the one that I made a mistake on, but I made a correction on the key.
Okay.
Mr. Yang, for natural log over, exponential, wouldn't it be approaching infinity?
Yes, so the idea is that they're both approaching infinity. But one is approaching infinity at a faster rate than the other.
Yeah.
So for instance, if I had, I'm just giving you a very exaggerated example. If I had 1 over 10 versus 2 over 100, and 3 over 1,000, and 4 over 1,000,000. I mean, they're both approaching infinity, but this denominator is growing at such a faster rate, my expression is still moving towards zero.
Yeah,
And we're saying for that natural log of x, when, isn't the top one going faster?
No, logs is the slowest,
oh.
then radical. So if you
Okay.
think about logs, logs is
Oh, wait.
is
Okay,
slow.
okay.
Exponential is really fast.
All right, thank you. Thank you, Mr. Yang.
Okay, yeah.
They'll be good.
Okay.
Thank you, Mr. Yang, so.
You have another day, right? You're gonna take.
Yeah, my big thing is just reviewing the things that I forget, like arc and
Yeah,
what
Yeah.
ln of 1 is, and you know, the.
right. But you have your calculator. That can help. Right. Yeah.
Okay,
But it's still good to know those
yes,
things.
yeah, we'll just review.
Yeah. This
Uh-huh.
is right here, that's.
Right. So if I'm looking at the graph here,
Yeah.
I need to find these in. That's the starting x value. This is the end.
Yeah, I looked.
So if I set the equations equal to each other.
Thursday and Friday this week.
I set it to 5:30.
But if I set the equation equal to each other, negative x squared is equal to negative 4. I get x squared equals 4, so that's equal to plus or minus 2. So those are my values. That's the given. Yeah.
So Sean and I are doing like